Okay, good. So, welcome everyone to our usual Wednesday ITMP seminar. And today we have Rostom Karsanov from the Moscow State University, from the Faculty of Physics, who will tell us about gauge supergravities and solutions with a Killing tensor. Rostom.
Thank you. I'm very glad to be here and present the results of my research. My presentation will be based on recently published article written together with my scientific advisor Dmitry Maxwell-dilaton-axion, and it is devoted to the study of exact solutions in gauge supergravity theories. So my talk will consist on two big parts. First, we will discuss the theory which we will consider. We will derive the equations of motion and choose the simplest form of the equations of the independent system equations of the system, and provide a motivation for the choice of the function which parameterize our fields of the theory. Then we will go into the second part where we will complete the integration of the equations, first for ungauged theory and then for the gauged version of the theory. And we'll provide a investigation of obtained solutions, and then we will make a conclusions. So let me start from motivation. So why do we even have to try to find exact solutions in supergravity theories? So the first reason is related to the fact that the theoretical study of ultra-compact cosmic objects is now one of the most relevant areas in physics due to the emergence of new channels of astrophysical observations, such as the interferometry of very long baseline and gravitational wave astronomy. And the possible deviations from the general relativity are associated with the supergravity or superstring theory as the models with deep theoretical motivation. One more important reason to consider these theories is actually related to the fact that in bosonic sector, these theories can be considered as the scalar vector tensor series with a wide range of Lagrangian. So we can find the solutions with big amount of free parameters and use these parameters in order to describe different ultra-compact objects. Also, in gauged supergravities, the black holes have a AdS asymptotic, so they are sought after in holographic models. And one more actually technical reason to consider this theories is related to the fact that apart from the Einstein-Maxwell theory, all the previously known black holes with AdS asymptotics were obtained by just guesswork and then proving these solutions by substitution into the equations of motion. So it would be nice to obtain these solutions by direct integration of the equations of the system or the theory, and also maybe even generalize those solutions. So we will start by considering the ansatz for the metric. So we will consider the metric in the so-called Benetti-Francavilla ansatz. And this ansatz is given on the slide. And it is defined fully by the functions A2, A23, and B2, B23, where the functions A are just functions of the variable R, and the functions B are just functions of variable Y. We will also impose the condition for separability of variables in the Klein-Gordon equation for the real scalar field, and this condition is given by the formula 2. So we see that our metric is fully described by the functions A2, A23, and B2, B23, and also by just investigation of this metric, we see that there are two commuting King-link vectors which correspond to the translations along the time coordinate and the coordinate field. So we will provide our calculations in tetrad formalism. So we consider the tetrad associated with our metric parametrization.
Sorry,
It's
Rostom, for interrupting you. I have a question. Why is this particular, why is, so in the previous slide, why do we take such particular form for sigma? Because, well, I can see that you're considering B axisymmetric solutions, but what are
uh,
the deep motivations behind it?
so such a you mean this, right?
Yes.
So this condition guarantees the separation of the variables in Klein-Gordon equation for the real scalar field. And we impose this condition because in Einstein-Maxwell theory, the similar condition uh, led to the separation of variables in the Einstein equations.
Uh-huh. And in general, the Benenzi-Francaviglia ansatz, is it so basically what does it correspond to? Like what are the deep motivations behind it?
So in general, you mean, yes?
Yes, in general.
So as I know, in general, the Benenti-Francavilla ansatz leads to the existence of conformal killing tensor, actually, which is slice reducible, which means that it becomes trivial at the slices defined by constant R or constant Y. So it is used uh, in the study of the photon orbits in the Kerr spacetime.
Mhm.
And actually, these restrictions uh, make our P90 ansatz look the same as the Carter ansatz, which we will discuss.
Thanks.
So we consider the tetrad formalism. We introduce tetrad one forms defined at on the slide. And if we write our metric in terms of these tetrad bodies, we obtain that we have just the metric of the Minkowski spacetime. Then we have the expression for the tetrad components of Ricci tensor in terms of so-called Ricci rotation coefficients, lambda, which are in their turn defined by the commutators of basis vectors. And one can show by direct calculation that the only non-vanishing components of such a quantities are given at the bottom of the slide, and substituting them into the expression for the tetrad components of the Ricci tensor, we obtain such a table of their components. And although they look very massive, we will see that there are such combinations of the Einstein equations that a lot of terms here will cancel out. So consider now the action of the theory. We will consider the theory Einstein-Maxwell-dilaton-axion, which is a consistent truncation of the bosonic part of n equals 4 gauge supergravity. And its action is given on the slide. And we see that it consists of first the usual Einstein-Hilbert term, then there are also two scalar fields phi and kappa, dilaton and axion. There are some scalar potential, and also there are abelian vector field, which interacts linearly with our scalars. And the ungauged EMDA theory corresponds to the limit when L goes to infinity. So when we will obtain the theory without a scalar potential. We will also introduce the complex field, which is often called axi-dilaton and is defined by such an expression. And we can rewrite our action in the complex form, also introducing the self-dual Maxwell field. Now, varying this action with respect to the axi-dilaton, we obtain the equation of motion for it. Varying it with respect to the metric, we obtain the tetrad components of the Ricci of the Einstein equations, and they are given on the slide. And we introduce two energy momentum tensors. First, the scalar energy momentum tensor, and the usual energy momentum tensor for electromagnetic field. Now we will consider 1-2 component of these equations, and they will actually lead to a simple linear equation with separated variables. And so we see from this equation that the functions a23 and b23 must be just the polynomials of the second degree of corresponding variables. And we can perform the coordinate shifts of coordinates r and y in order to set the linear terms in these functions to 0. And also we can use the invariance of the metric with respect to the rescaling of coordinates t and phi to set c equals to unity and b equals to 1. And then for the functions a23 and b23, we have such a nice expressions. And then the quantity sigma, which actually corresponds to the square root of the minus determinant of the metric, is given by such an expression. One more simple equation can be obtained from the difference of 1-1 and 2-2 components of the Einstein equations. And we notice that this equation becomes linear in the ungauged limit. Also, the sum of 1-1 and 3 components and the difference of 2-2 and 4-4 components leads us to such a equations. And also we can consider 3-4 components, which is the equation on the axisymmetric only, and it gives us such an equation. Now, if we watch carefully on the last 3 equations, we will obtain that our axisymmetric must be a holonomic function, and also it must satisfy the Laplace equation. But then the axisymmetric will be a single-valued function and must be represented as a fractional linear transformation. So we will choose this transformation to have such a form. And actually, one can see that the constant z infinity corresponds to the asymptotic values of axion and dilaton. And if we want to consider them vanishing at special infinity, we consider z infinity to be just high. And for axisymmetric, we have such a fractional linear transformation defined by only just 2 complex numbers C1 and C2. Also, we have to choose an ansatz for our Maxwell field, and the ansatz for it was first found by Carter in his famous work of 1968, and is given in tetrad basis by 2 components, and is defined by just 2 functions r big and y big. So, which are also the functions of r or y correspondingly. And one can check that such a one form leads to the separation of the Hamiltonian-Jacobi equations for the charged particle, and also to the separation of variables in the Klein-Gordon equation for the complex scalar field. Now we can find the tetrad components of the Maxwell field strength by just calculating the external derivative of our potential one form. And we will obtain that there are only 2 non-vanishing components, namely F13 and F24. And they are given on the slide, and also they are related with the Hodge duals F tilde 24 and F tilde 13. So such a parametrization leads us to the fact that in the whole system of modified Maxwell equations and Bianchi identities, only 2 Maxwell equations are not satisfied by default, namely the ones given at the bottom of the slide. So now we have to motivate the choice of ansatz for our functions r and y, which parameterize our vector field. So in order to do this, we can notice that our Maxwell field strength components can be represented as a partial derivatives of some a scalar combination of these functions, which we'll call the scalar potential. And then we have a freedom to make a gauge transformations where we just add a constant number to this scalar potential. And also from the difference of the independent Maxwell equations with appropriate coefficients, one can obtain such a nice linear differential equation with separated variables. And here we see that the functions R and Y also have to be the polynomials of the second degree of corresponding variables, but they will contain the same multiplier at the higher power of these polynomials. And using this gauge transformation, we can remove the higher powers of these functions and consider them to be just a linear functions. We will consider them to be given by the equation 36. And it turns out that in the whole system of the equations of motion of the theory, there are one more independent Einstein equation, and we can choose it to be, we can choose it by different ways. And we choose it to be the sum of 1, 1, and 2, 2 components of the Einstein equations. And in order to write the sum of Ricci tensor components in a convenient way, we introduce a gravitational potential P. And in terms of this potential, this remaining equation is given by such an expression, which looks like a Laplace equation with the source defined by the Maxwell field. So we have rewritten all the independent equations of the motion of our theory, and we will see that they allow the separation of variables. So now we will provide a complete integration of the equations for the ungauged EMDA theory. So as we discussed, the difference of 1, 1 and 2, 2 components of Einstein equations gives us, ungauged limit gives us a linear equation. So the functions a2 and b2 must be also the polynomials of the second degree of corresponding variables, and we choose them to be given by such expressions. And if we consider the time component of the metric, then at partial infinity, we will obtain that it is given by such expressions. So if you want to consider the spacetime to be locally flat, then we have to set lambda equal to 1, and also identify our integration constant a1 to a Schwarzschild mass. So further, the recipe to obtain the solution is the following. So we will take our functions and substitute them step by step into the equations of motions that we have derived. And at each step, we will extract some constraints on our coefficients of polynomials and substitute them into the second step, into the second equation. And thus, if we do this first for the sum of the 1, 1 and the 3 components of Einstein equations, then for the Maxwell equations, and finally for the remaining Einstein equations, we will obtain such constraints on our coefficients. And actually, there will be one more independent equation, which is the equation of motion for the oxide dilaton. But one can check that substitution of all these constraints into this equation satisfies it by default. So we integrated the whole system of equations. So we then can write our functions defining the metric in such a form where the constants delta 0 and delta 1 were just introduced in order to satisfy the constraints following from the equations. And it turns out that in order to obtain a non-singular static limit, one has to perform a coordinate shifts of the coordinate y and make a redefinition of the free parameters. And after doing this, we have to interpret our constants delta 0 and delta 1. And in order to do this, we consider the equatorial plane at spatial infinity and consider the metric of given by the coordinates r and y, r and phi. And we will see that the parameter delta 1 introduces the conical singularity in our solution, which in turn can be interpreted as the cosmic string. So in order to remove the cosmic string, one has to put delta 1 equals to 1. But for now, we will keep it arbitrary. So in order to determine the physical meaning of the constants b1 and delta 0, we consider the rotational function omega and consider it at the spatial infinity. And one obtains that in order to introduce a node parameter, we have to choose b1 equals to node divided by a, which is a rotational parameter. And then for the rotation function, we obtain such an expression. And we see that the combination of parameters delta 0 plus a delta 1 define as the parameter which can change the configuration of the Misner strings. So choosing them equal by 1 on -1, we can remove either north or south strings, but we want to set them symmetric. So we set this parameter equal to 0. So we choose delta 0 to be minus a multiplied by delta 1. So in this case, also removing the cosmic string, we set delta 1 equals to 1 and delta 0 equals to minus a. Then the final form of the solution of the ungauged theory is given on the slide. And here we also introduce the real charge and the real the absolute value of the complex mass, which is m plus I multiplied by E, and also the absolute value of the dilaton charge, which, as we see, is related to the electromagnetic charge. So it was checked that this solution coincides with the solution previously found by the Ehlers-Harrison transformations using the isometry of the three-dimensional sigma model. So now we can investigate this solution. We can find the values of the radial coordinate corresponding to ergo region by the condition that the Killing tensor dt becomes null at the surface. So we can also find the radial, the values of the radial coordinate corresponding to the horizons, and also find the angular velocity of the horizon. So now calculating the, for example, scalar curvature, Kretschmann invariant, or the square of the Ricci tensor, one can obtain that the curvature singularity corresponds to the equation sigma equals to 0. And actually, this equation gives us an equation of the circle of the radii d. Here we also introduced a new variable x, which is a cosine theta plus n. And as we see, this new coordinate is compact. So the allowed region for us is in the graphic where the axes are defined by x and r. We have that r runs from 0 to infinity and x runs in some limited range. So if this area has an intersection with the circle of radii d, then we obtain that this intersection corresponds to the singularity. So we have a possibility to uplift this area up or to put it down in order to not have such an intersection and in order not to have such a singularity. And actually, apart from the Kerr solution, where the singularity has the form of the circle, as we see, we will have some kind of two-surface which is singular. So now we can provide an investigation. So if we consider the case when the absolute value of the new parameter is larger than the rotation parameter, one can obtain the condition for the absence of the singularity at all. So if we see, for example, at this watch, for example, of this graphic, we see that if n is larger than a, then we can adjust the value of the new parameter in order x minimum to be larger than d. So this interval will not have a intersection with the interval from minus d to d. And independently of the sign of the node parameter, one can obtain such a condition on the electric charge, which guarantees the absence of the singularity. Now we consider the second case, when the absolute value of the node parameter is where the rotation parameter is larger than the absolute value of the node parameter, and then the singularity will be represented by part of the circle in such a way that the point x equals 0 will be included. So the largest value of the radial coordinate corresponding to the singularity will be r just equal by d. So in order to not have a naked singularity, we have to impose the condition that the value of the outer event horizon is larger than the value of the radial coordinate corresponding to the singularity. And we can write this inequality using the connection of dilaton charge with the electromagnetic charges in such a way. And we have to distinguish between two cases. First, we consider the overcharged solution, and then we can take the square of this inequality and obtain such a inequality. So we assume that our rotation parameter is larger than the node parameter, so this inequality cannot be satisfied. So in the case of the overcharged solution, we always have a naked singularity. So now we consider the second case, and actually we can obtain the solution of the constraints on the mass and the electric charges, such as in the case of the when the rotation parameter is larger than the node parameter, there will be not a naked singularity. So a more detailed investigation can be provided in the static limit. So if we consider the case of vanishing rotation parameter, for the expressions defining the horizons, we have such expression. For the singularity, we have such relation. And in order to establish the relative position of the surfaces, we consider the value of the expression given by the difference of the squares of these two surfaces. So we would like this parameter to remain positive in order to not have a naked singularity. And if we write this expression throughout the parameters of our solution using the relation of dilaton charge to the electromagnetic charges, we obtain such a relation. And we again have to distinguish between two cases. First is again the overcharged solution, and we obtain that in this case such expansion always have to be negative, because as we assumed this bracket will be positive, and this bracket is always positive also. So we have a naked singularity. So in the second case, we have such relation for this quantity. And we see that as long as node parameter is not equal to 0, the singularity is located under both the horizons. And in the case of vanishing node parameter, the position of singularity coincides with the position of the inner horizon. Now we can provide a investigation of the absence of the horizon at all. So the condition which guarantees the absence of the horizon is given on the slide. And actually, it is given by, 1 second, it is given by the demanding that this square root becomes imaginary. So we consider such a inequality. We can solve it as the inequality on the electric charge using, again, the relation of dilaton charge with the electric charges. And its solution is given by this inequality, which we can write in a convenient way by such an expression where we introduced a quantity gamma which runs from -1 to 1. And for a solution to be a wormhole, one has to impose the condition that the quantity sigma is non-zero and positive definite everywhere. And as we have seen, in the case when the absolute value of the node parameter is less than the rotation parameter, there is always a ring singularity. So we must consider the opposite possibility. And in this case, the sufficient condition for sigma to remain non-zero is given by such an inequality. And here we again distinguish between two cases, namely the positive node parameter and negative node parameter. And actually, in these both cases, one obtains that we cannot satisfy the condition for the absence of the singularity along with the condition of the absence of the horizon. So we cannot describe so our solution cannot describe the traceable wormhole configuration. So now we will go into details of completing the integration of the gauged EMDA theory. The main difference in the process of solving the system for this variant of the theory is related to the fact that the functions a2 and b2 now must be polynomials of fourth degree, which actually comes from the difference of 1 and 2 components of Einstein equations. And by solving the equations of motions exactly in the same order as in ungauged theory and extracting the conditions of the coefficients, one obtains such a solution defining the metric. And in order to have a regular static limit, we also have to make a coordinate shifts of the coordinate y and the redefinitions of our free parameters, which are given on the slide. And then we will obtain such a general solution for the gauged theory. And also here that the functions a2 and b2 are functions of fourth degree. So we can provide the investigation of this solution. And in order to do this, we write the metric in such a form, which is actually the form which is used for dimensional time-lag dimensional reduction. So this form allows to extract the three-dimensional metric, and we are interested in the metric spanned by the coordinates y and phi. And we will consider the static case and the special infinity. So R will go to infinity. Then we will obtain for this metric such expression, and calculating the Gaussian curvature of such a surface, we obtain that it is proportional to our parameter lambda. and then choosing lambda to have a different signs, we can obtain three different topologies of the surface spanned by these two coordinates. Namely, we can obtain the spherical topology, the hyperbolic topology, and the flat topology. Also, these three topologies are common feature of the ADS black holes. And also, such a classification can be provided in the case of the when the rotation parameter is not zero, but it is more complicated. We can also find the values of radial coordinates corresponding to the extremal value of the extremal horizon. And in order to do this, one has to solve now the quartic equation, which is given on the slide. And we can write the roots of this equation using the Ferrari's formula. And the real roots of this equation are given by such expression. And y1 here is the root of the cubic resolvent equation. But instead of solving these equations, we can find the condition of extremality from the Ferrari's formula and find the value of y1 corresponding to extremal limit. And then substitute it into the resolvent equation and consider it to be the equation on the mass parameter. And then we can find the value of mass parameter, which corresponds to the extremal limit. And then substitute it into the equation, into this expression, we will obtain the extremal horizon. So if one do this, we will obtain such expressions for the radial coordinate of the extremal horizon and the extremal mass. And it was checked that in particular cases, such expressions can coincide with analogous quantities for Kerr-Sen-AdS black holes and also for Kerr-Newman-Knut-AdS black holes. So now we make a conclusion. So as a conclusion, we can say that we developed a method that makes it possible to find the solutions with the Killing tensor in cold supergravity theories. For the first time, we justified the choice of the axisymmetric field to have the form of the fractional linear transformation. For ungauged EMDA theory, we found the most general solution with the Killing tensor. We found the conditions for the absence of naked singularities and shown that the solution cannot describe the wormhole. For gauged EMDA theory, for the first time, we found the analytical solution by direct integrating the equations of motion. And it was shown that the obtained solution is the generalization of previously guessed solutions of gauged EMDA theory. So thank you, and I would like to answer if there are any questions.
So I'm not an expert, but probably you can clarify how is it compatible with things like null-Hare theorem?
So there is no such thing, as I know, there is no such thing as null-Hare theorem for the EMDA theory. So.
And what was the original setup? So
the original action, you mean?
no, I mean the original. I don't know if you remember the original setup for which the null-Hare theorem was proven. So I'm not an expert, but I thought that the statement is rather general.
Okay, I know that this theorem is can be applied to the, for example, vacuum theory, or vacuum gravity or the electrovacuum gravity, but I'm not sure that it can be applied to the solutions of the EMDA theory.
Okay, thank you. Okay, so I have another question. So, do you know how does it fit the solutions that you found in some like other classifications like Petrov? What's the Petrov type?
Yes, actually, this form of Benenti-ansatz, which I discussed at the beginning, it has the type 1, so-called type 1, which shares the same features as the vacuum type D, which means congruences of isotropic geodesics without shear. But now the Ricci tensor is not zero, as in the case of vacuum gravity. So it is type 1
Okay, because it's not just
in
gravity.
Petrov classification.
Yeah, okay, I see. And
Yes,
is it
yes.
Kerr-Schild? Is it Kerr-Schild? Can you write it as Kerr-Schild form?
What do you mean? You mean coordinates?
Well, there is a Kerr-Schild ansatz for the metric. No, I just like know a couple of things. Like I'm not like knowledgeable about solving Einstein equation, but I know that there are some like standard ansatz that people use, and one of the approaches is to look for solutions in the Kerr-Schild form.
Actually, I don't know.
Okay.
Can it be written in Kerr-Schild form, but the Benetti-Francavilla form, which is given by this ansatz.
Okay, thank you.
Let me comment on the equations which were posed by Dmitry. First about No-Hair theorem. Actually, this theory possesses scalar fields, and scalar fields are on zero outside the horizon, which can be in pure Einstein scalar theories. It is violated by No-Hair theorem. It's one of the most known No-Hair theorems, the scalar field outside the horizons, non-singular, is impossible. But here it is so-called secondary scalar fields because it is just accompanying a Maxwell field. And if the scalar charge is not a free parameter, you can construct more general solution where the scalar charge is free parameter, but it will be singular then unless the special restrictions which are satisfied here. It is the value of dilaton charge determined by the electric and magnetic charge of the solution. So it is a kind of secondary hair. But it is a well-known story, so there is nothing new here. The second question was about Kerr-Schild. Kerr-Schild is also possible here, but it does not add something new because the metric has a Kerr form, actually. The obtained metric finally has a Kerr form, but with different parameterization of metric functions. And that's the point. And there was a third question I forgot already.
About the Petrov classification.
Petrov type. Yeah, the first, the story is the following. So the Benenti-ansatz is something which gives the metric possessing commuting killing vectors, dt, d phi, and the killing tensor of the second rank. And it is irreducible, and it is given explicitly in terms of these Benenti-Francavilla coefficients A and B. But general type of this solution is 1, so it is not algebraically special. But then if one restricts, one make several restrictions. First is that the form of Newman-Penrose tetrad is simplified by square roots. There are square roots, which make you something terrible. You cannot see anything. So it is clear that it is type 1, but you cannot say more than that. But then it was actually some of solution in supergravity black holes are already known by using different techniques used by dimensional reduction and Ehlers-Harrison transformations. And from this solution can be established that there are some hidden symmetries apart of killing tensor. These symmetries are existence of null geodesic congruence without shear. And in classical gravity, in vacuum and electrovacuum gravity, this is known by there is a Goldberg-Sachs theorem, famous Goldberg-Sachs theorem, which guarantees that then if there is such properties, but for vacuum and electrovacuum, existence of null shear-free geodesic congruences, and then it will be type D, and it is just what is observed in Maxwell theory, Einstein-Maxwell and vacuum Einstein. So Kerr-Newman is type D, but here this theorem does not work because the matter is different. It is not just Einstein-Maxwell. Maxwell energy momentum tensor has some special symmetries. Apart from trace zero, it has also symmetries between components. And it is just these relations ensure validity of Goldberg-Sachs theorem. But here it doesn't work. So we obtained a generalization in a previous paper, which was referred to with Kulitsky. We found that in this case, with scalar fields, which is typical for supergravity, the type is 1, but is not the most general one. It is such a type 1 which has in the degenerate case, so there are some restrictions on parameters when you can find the subspace which is algebraically special. Algebraically special is different. It may be type 2, type 3, type D in particular. But here is only type D. So we have some subspace of 1, which is maybe thought as just the minimal extension of type D. And this may be the reason. And then we have a restriction on Benanti coefficients. The first restriction, it is relation between a1, A3, and A3, A4, and A5, and B also. And this is already was assumed in this paper. So it is just Benanti with restriction to have such null geodesic shear-free congruences. Well, and then another restriction is for determinant. It ensures the validity, the separation of variables in Klein-Gordon equation. It is another restriction. So after all those restrictions, this remains to be type 1. But the metric, only the metric, assumes the form of Carter. And Carter called this integrable spacetimes when you can solve directly Einstein equations and Einstein-Maxwell equations. And what here is shown is just that we can extend this Carter argument to supergravities, which all supergravities, we don't think so, but at least this EMDA with one vector field, it is okay. And which is a advantage that we have sigma model technique to construct solutions by transforming the Kerr metric just. It does not work in gauge case and with scalar potential. But this method works with scalar potentials. Just the solutions were known, but just by some guesswork, comparing with ADS Maxwell field, ADS solution with Maxwell field, pure Maxwell field. So this technique is just the only known way so far to solve Einstein equations and other field equations in supergravities, which gives you analytical solution.